In this video, we're going to pick up where we left off in the previous video by doing a couple of examples of the hypothesis test. So for this first example, we're going to consider a data set of diastolic blood pressure readings from subpopulations of patients with a new dieting protocol. Now, previously, patients in the subpopulation showed an average DBP of 108.7, and again, this is a mean. And we are seeking to determine if this has changed using a type 1 error rate, or alpha, of 0.10, so 10%. It's going to be our false positive rate. We have our data set here. So looking at this data set, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 observations that will be true. All right, so the first things first, let's set up these hypotheses. Now, sometimes when working through this, hypotheses seem a little bit silly or superfluous, but these are actually really helpful with more complex steps because they really articulate our starting beliefs, that null hypothesis, and what we're going to believe if we can gather enough evidence to convince us to change away from that null hypothesis. So in this case, because we're just looking for a change, our alternative hypothesis is going to be not equal to that value, and then that null hypothesis is going to be equal to that default value. So we're just trying to see, did it change? Our default value is no, it didn't change. We're still at that same value that we've been at. And the new value, if we gather enough evidence to convince us otherwise, is going to be that yes, there is a difference between our mean, represented by that character mu, and the classic DBP of 108.7. So don't forget, we need the point estimate, standard error, and critical values to pull together our test statistic. So at this stage, we also have enough information to ask the computer for the critical values. So what we need to ask for the critical values is the error level percent, which is 10%. So we're going to ask the computer for cuts 5% on top, 5% on bottom, which sum together for the total error rate of the problem to be 10%, or 0.10 for that alpha number. And so we can, at this very early stage, after we set the degree of confidence, go on and calculate those critical values from here. Going on and doing that for us, for the critical value calculation, this is going to be 1.645 for a 10% error rate. Again, 5%, the plus is the top end cutoff on a curve, positive 1.645, and that cuts off the top 5% of the curve. And then the bottom is negative 1.645, that cuts off the bottom 5% of the curve. And I'll note that this is always going to be plus or minus the same number with symmetric distribution, so our normal distribution, our t-distribution. All right, so now we need to go do the calculations for the test statistic with the point error and, the point estimate and the standard error. So remember our equation, we take that point estimate, x bar, we subtract the null hypothesized mean value, and then divide by that standard error value, sigma, divided by the square root of n. So for this, again, I love to just look at plugging in the values that we need. So we have 1, 2, 3, 4 values that we need to pull out of the data. The mu we'll start with, this always comes from the null hypothesis. So in the null hypothesis, we have hypothesized as our default belief that mu is 108.7. So this mu value is going to come from that null hypothesis. And it's important to realize, again, that we are putting our data, the test statistic is putting our data on the scale of the distribution, but that distribution comes from the null hypothesis. And this is one of the places that that's incorporated. So next we'll find X bar, so this should have a full bar over it, I'm sorry. X bar, sigma, the population standard deviation, or S, the sample standard deviation, and N from the data. So you can go on and try that if you'd like. In this case, we have X bar as 100.43 from that data. S, the sample estimate of sigma, or sigma hat, which is another way to denote the sample estimate, is 10.6, and N equals 14. So if you're working through this, go on and pause, go back to that data set, and practice that to see if you're getting these same answers using Excel. So if this is feeling complex, go on and close your ears. But for those of you who this is making sense, we'd normally use a t-distribution with a degrees of freedom of n minus 1, or 14 minus 1 equals 13 in this case, because we're estimating this standard deviation from the data. But in this case, we're keeping with the normal distribution just to keep things simple. It's important to note that with the larger data sets that we use outside of the class examples, the differences are minimal. So if you get above maybe 20 or 30, the differences are on the scale of thousandths or 10 thousandths or 100 thousandths different. And so it's really not as important to account for that. Where it becomes much more important to use that particular distinction between T and Z comes with small sample data. So if you're using samples of just a few participants to try to run a statistical test, that actually becomes pretty important to make sure that you're using that T distribution instead of the Z distribution. But again, for most of the data sets that we're talking about dealing with in a healthcare administration context, we're just going to have much larger sample sizes, and this distinction is not relevant. All right, so when we plug this information in, again, this is our formula. We filled out where we found these values. Remember mu, the null hypothesis, X bar, sigma, or the sample standard deviation S, and N all came from data. And we plug these into the formula. We get our test statistic is negative 2.92. So if we remember what our critical values were, plus or minus 1.645, we can see that this negative 2.92 is lower than the lowest critical value. But let's go on and look at this graphically too. So because it's lower than the lowest critical value, we know this is a significant difference. But here we can see a graphic of this. So we see the critical values here, and then we have the test statistic down here, which is lower than the lowest critical value. So again, this is our area where we're saying this is outside of the range. This is way out. Remember, we talked about that last time, way out. And so this is indicative that the data are not aligning with our null hypothesis. This is kind of where we'd expect it to fall in if our null hypothesis was true, and the data just don't align with that null hypothesis distribution. So if I have to pick between the data and the null hypothesis distribution, well, I being a responsible decision maker, am not just going to die on my hill and say, oh no, I'm sticking with my default belief no matter what. I'm going to change my mind to be what the data indicates. Again, this is all part of a broader logical argument, but that's the idea behind statistical decision-making using the hypothesis tests. I should note here, and it's always important to note when you make the decision, the degree of confidence, because this doesn't prove anything. This is just stating that this is what we found. So the degree of confidence that we have here, well, we had that 10% error rate, so we have 90% confidence in this decision. All right, so for the p-value approach, you're seeing that this image looks very similar, but you'll see we don't have cutoffs or critical values in the p-value approach. We have the area that's shaded, that's more extreme than our test statistic. So we do this at the on both ends of the distribution, and this isn't shown here, but we have this shaded, and you can barely see it on here. that the bottom part is shaded in red of the area that's more extreme than the test statistic. Again, I don't show it on the graphic. Maybe I can really try to draw it. But this is also true at the top end. So we're actually adding together both of these shaded parts, both on the bottom end and the top end, to come up with the total area that's more extreme than the test statistic. And again, because we're looking at the top and the bottom, it's more extreme on both sides. This is the area that's more extreme on the bottom side, and this poorly shaded area is the area that's more extreme on the top end. Now, this will always work out to be double this shaded area. So if we ask the area manually in a stat software to be multiplied by 2, then we're going to get the correct value. I should note when we're calculating like a statistic via a statistical software, so we're not manually finding areas under curves, but instead we're just asking it to run the statistical test and give us a p-value back, which is very common to do. The area is already doubled in the p-value that it provides back. So it's not something to worry about in the mid or long term, though it is something that you'll practice in this section. So again, this is found via calculus. It's area under the curve. If we ask software what this is, we get 0.0017 for the area under the bottom curve. And doubling this to account for the top end, we get 0.0034. So our p-value for this problem is 0.0034. And so with our p-value, 0.0034, with our p-value, we compare that to alpha. And remember, our alpha level for this is 0.10. Because alpha is 0.10, p is less than that alpha value. So alpha is 0.10. P is a smaller number than alpha. P is a smaller number than alpha. P smaller than alpha. And so this has met our criterion as our data are quote unquote way out there under that default belief. So our data and default belief don't seem to align with one another. And again, if we've collected the data via a format that we feel comfortable basing decisions on, it's been collected in a way that seems to us to be reasonable and representative, then we're going to trust the data that we've collected more than our default belief. And so when those two disagree, we'll tend to go the direction the data suggests as opposed to the direction our default belief suggests, which in this case means we're rejecting that default belief or rejecting the null hypothesis. So when that p-value is lower than alpha, this is when we reject that null hypothesis. All right, so our conclusion, again, is to reject the null hypothesis. And it's important to realize that whenever we reject the null hypothesis, well, we have something else that comes out of this. So we've written not just a null hypothesis, but a null and an alternative hypothesis. So rejecting the null hypothesis, we're going to do that in favor of the alternative hypothesis. So remember what these are. We had the null hypothesis that mu was equal to 108.7, and that's what we're choosing to reject. So we don't think mu is 108.7. So the alternative, remember, was just crossing through that. Mu is not equal to 108.7. And so for this case, we're not just rejecting the null, we're rejecting the null in favor of another option. Put in more practical terms, this means that we have evidence to believe that the mean diastolic blood pressure is not 108.7 as it was before in this particular subpopulation. That is, we have evidence to believe that the subpopulation has changed. And again, it's important to realize that this may or may not go in the direction that we think. So we would want to go and look at and say, okay, well, what was the sample value to see, did it go up, did it go down, did it go in the direction that we changed. So we have seen that it's different. And all that we would do to figure that out is just to go look at the sample average DBP and say, okay, well, it looks like it's gone up. So that's something that we would go and examine to determine the direction of the change. And that's something I do all the time. I'll run a test. It'll come back as statistically significant. And I'll say, okay, well, did it go in the direction that we thought? And so check on that. So again, in this case, we conclude the program is related to a statistically significant reduction in DBP. And again, where does the reduction come from? Well, the reduction comes from going and looking at the sample value in comparison to this null value. The sample value is lower. So we have evidence to believe our data or our null hypothesis is wrong. The question is, well, in which direction? And so we would look at the sample data to determine that. I'll note a couple of things about this conclusion. First, we use related to instead of causes to avoid making a causal claim. Remember, causal claims are associated with the study design, and because we don't know the study design, we don't want to assume it. This particular study design is very unlikely that this was experimental in nature. Again, the reduction comes from the comparison of the sample mean to that original hypothesis. And so we just do that comparison to determine, was this a significant reduction or a significant increase in DBP? We use statistically significant because the test was way out from that null distribution. So if it wasn't way out from the null distribution, we would say the program is not related to a statistically significant reduction in DBP, or that we don't have evidence to conclude that the program is related to a reduction in DBP. So again, I can't emphasize this enough. The sample mean is clearly lower. The sample mean was like 100. It's clearly lower than the null hypothesized value. So why are we doing the test? Well, again, we're not doing a test to determine if the sample mean is lower. The reason we're doing the test is to determine if this is enough evidence to think that the population mean is lower than this. So our goal is not to make a conclusion about the sample of 14 individuals that we looked at earlier. Our goal is to make a conclusion about the population that sample represents, and to determine if the evidence presented by that sample is enough to convince me that the population diastolic blood pressure has changed. And again, depending on how the program was set up, then we would say that the program is either associated or the program caused that change in diastolic blood pressure. All right, well, now it's time for you to try one. So for your try, go on and try doing the below data on staff recruitment after a new HR manager was hired. So we had this new HR manager, and we're looking at, well, it's a bit of a complex situation, but in this problem, we're just going to be looking at the age of the new staff that are recruited after that management change. So previously, staff that have been recruited are at an average age of, let's say, 26, 27 years old, and we want to be 95% confident in our decision. So we want to determine if this has changed one way or the other. We're hiring younger now, we're hiring older now, with 95% confidence. So take a moment to think about, what will alpha be if I want to be 95% confident? That is, what will my error rate be if I want to be 95% confident? So right now, we don't have the software for the critical value. That'll be later potentially. So we're going to use plus or minus 1.96 for the purposes of this example, so that you don't have to hunt around for that. So go on, take a moment, pause the video, and work through this problem. All right. So coming back to it, let's see how this went. So for me, my null and alternative hypothesis, where the mean is the same as it was under the previous management, or the mean age has changed under the previous management. When I calculate out the mean sample standard deviation and sample size, I get 30.69 for the mean, 4.82 for the sample standard deviation, and 13 for the sample size. Plugging all this into my formula, this turns out to be a positive 2.99 test statistic. And when I compare that to my critical value, this is bigger than the largest critical value. It counts as being, quote unquote, way out there. So this is a statistically significant difference between what my sample's telling me and that null hypothesis. So consider if software returned the p-value as 0.007 for this test, and it was already doubled, what would you conclude and why? So try interpreting this p-value and kind of writing up that interpretation. Go on and pause the video now and try interpreting the p-value component here. All right, coming back to it. See how that went. So again, for a critical value, it's clearly outside of the kind of typical region. It's way out there. And so we reject the null hypothesis. This is our null hypothesis distribution. And our data just doesn't seem to align very well with that null hypothesis. So we reject that null hypothesis in favor of that alternative. For the p-value approach, the same thing's happening here. We have a very small p-value, that 0.007. That is clearly less than alpha. And so again, we reject that null hypothesis because the data doesn't seem to align well with the distribution from our null hypothesis. So as a bit of an aside, glancing at your p-value can give you a hint as to how low your alpha could have been. So how confident you could have been in the conclusions. I will say that changing your level of confidence for your decision after looking at your data is kind of a no-no in statistics. That is, your confidence level should be set before the study. A fancy word for that is a priori. But this can be useful for determining confidence in future studies. Also, I'll say we do commonly report p-values in write-ups or in slides or in papers for others to see so that they can evaluate that level of confidence for themselves. All right, so our conclusion, again, via both critical value and p-value, and they're always going to agree, is to reject that null hypothesis in favor of the alternative. Again, what are we rejecting? We're rejecting that the mean age of hiring is 26.7, a value that we found from a previous staffing data. And so something has changed. We have evidence to believe that the mean age of staff that are being hired under this new manager is not 26.7. And again, the important thing that we can say here is going beyond the sample. So there could be pushback. Oh, well, that was just the people that you pulled from. That's just the sample. It could have been maybe it was just a low week or a high week. Well, to the degree that that sample is representative of the population, our statistical analysis lets us conclude that no, it's not just that there's a little bit of variability in the data, that we have evidence to believe that this is something more, that the population mean age is not 26.7. So our final conclusion, change in HR leadership is related to a statistically significant increase in the age of new employees. And again, we're using that same language. So it's so important, actually, with this case. So one thing is this isn't necessarily causal, right? This is just something that, it's unexpected. Maybe it's worth your time to look into. Maybe this is intentional. But you got to be pretty careful because there is just saying there is a relationship there doesn't mean that this A caused B. So for instance, one case where we might want to say this is we might want to say, well, there's changes in the hiring practices of this new HR leadership that's leading to this. That is, HR leadership is implementing policies that is causing different ages to be higher than what we had previously. And that is not necessarily supported here. Again, that causal claim is not necessarily supported here. What we can look at is to say, well, there does seem to be a relationship with this, and investigate that relationship further to determine if we can find the source or cause of that. And be very careful with causal claims. Very often what we have is supported to say relational claims. And that sounds kind of like a caveat, and it is in many ways, but the importance of this can't be overstated because I'll say commonly individuals want to make causal claims but have observational data. And this can ultimately lead to, often it can lead to claims that are just fine. The observation is indicative of an underlying causal relationship, but this can also just as easily turn into a relationship that is not causally related. It's indicating some additional variable that hasn't been accounted for in the study design or something else like that. And in that case, decisions made based on this information, assuming that it's causal, would be inaccurate and could lead to bad or decisions. Now, again, we can conclude that there is evidence that something has changed from previously to now. We just can't say that it is A or B or C based on what we know about the study design. All right, well, let's go on and close out with a summary of some of the information that we've talked about for hypothesis testing. So the idea behind hypothesis testing is we start with our default beliefs and we acknowledge those. Using those, we make a distribution, assuming our default beliefs are true. Ultimately, we place our data on the distribution, converting it into a test statistic, and then we compare our data, the test statistic, to the distribution and see, does that data seem to align with the distribution or not very much? We had two approaches to do this comparison in as objective of a way as possible. One was the critical value approach, where we compared the critical value cutoffs, the kind of reasonable region, and then ultimately our definition of being way out there, to the test statistic. And so if the data was way out from the distribution, then we rejected the null hypothesis. And if the data seemed to largely match with the distribution, we failed to reject the null hypothesis. That is, we kind of stuck with that null. The p-value approach, the last approach that we talked about for hypothesis testing, it involved a little bit more calculation. But again, it's handy. Back in the day, we didn't do this, of course, because of all the pain in calculating this integral by hand. But these days, computers can do that very quickly. And ultimately, we simply compare p to alpha. Now, if we're calculating that area, quote unquote, by hand, maybe using Excel or something, we do have to double that area to account for the fact that it could be more extreme in the opposite direction. But if software is doing it for us with a built-in test, it's automatically going to do that. And again, that's going to be very common in most stat software. It's just in class that we're going to talk about kind of doubling the area by hand. So don't worry, stress about that too much. It's really just for practice, realizing that that is going on behind the scenes, and to kind of help you work through and sink that down into your soul there. So ultimately, we've got p compared to alpha. If our p-value is less than alpha, that is that metric of alignment between the null hypothesis distribution and our data is low alignment, lower than our alpha threshold, then we reject that null hypothesis and go with that alternative hypothesis. Otherwise, if the p-value is bigger than alpha, then we fail to reject and just stick with that default view. This has been video working through the examples for the hypothesis test. In the next video, we'll go on and talk about confidence intervals.